Okay, so let us continue our discussion of differential equations. So the differential equation that I want us to look at in this recording is the exact ordinary differential equation, as you can see the title there. So the way I will approach it is that I only will try to relate this differential equation to what we are familiar with. So what we did in Math 2, because I think we still remember that, so we will actually understand what is going on here. Because basically also just the aim here is to actually understand what differential equation that you are working with, and simply just get a solution. My focus will be in discussing the technique of getting the solution. So I mention this because there is another approach that we can have when discussing this differential equation, which will actually include things like the contour lines in multivariable calculus, where we have some three-dimensional space and we are plotting curves there. You introduce a plane, say z is equal to a constant, then you see now that you can actually have some form of contour lines cutting that shape, etc., etc. I will not go there because, of course, it's not something that we have done. So let us just enjoy ourselves with what we are familiar with. Maybe if we have done that part of calculus, I was going to go there, but since we have not done that calculus, I'll just stick to what we know. Okay. So what do we have here? Again, let us try to go back to Math 2, something that we have covered in the previous course. So we have discussed functions of this kind, right? So when we in Math 2, we tried to perform partial differentiation in these kind of functions, and then let us try to get both of these partial derivatives that we can get for this kind of a function. It only have two variables. So what could be the first partial derivative here? You will get, with respect to x, is equal to partial derivative, then f of xy. The next thing that you can get also is the partial derivative with respect to y. Sorry, with respect to y now, then is equal to partial derivative with respect to y, f of xy. Good. After we appreciated the concept of partial differentiation, then we went further. Again in Math 2, we tried to show a real-life situation where partial differentiation can possibly be applied. We tried to find some changes in volumes, some changes in areas. So this was a real-life application where partial derivative could potentially be used. And what concepts did we then apply these concepts of partial differentiation? We applied it in Math 2 in some small changes. So what did we have? We had, for instance, a delta z, if I may use it as z. Then we said delta z was equal to, if I may use the z again, just to take you back, delta x plus delta z, so delta y, then delta y. So what we see now is that they are the partial derivatives, which what we are talking about. But what is actually happening now is that this partial derivative, they assist in getting the change into this variable z, which is now a full change. It's not just per variable change, but it's a full change to the variable z here, which is the main function. We further improved this formula into getting the rate of change, which could also be the rate of change into z, which was like this, obviously the dx, so it's a plus dz, dy here over dt. So which was giving us the more detailed version of how the change is happening, the rate of change, the small pieces of change per time, which could be seconds. Okay, so this is what we did. So what do we see here? So basically this equation here that we have here giving us this full change, we have an equation in calculus which is called a differential. That is where I'm going. So a differential is basically the full change into the function, which basically incorporates all the little changes that are happening in the variables of the function. Right? So if we want to get a differential of our special variable z here, so what will be it like? So the differential of z in this situation, it will be dz is equal to then the partial derivative with respect to x dx plus the partial derivative with respect to y dy. Right? So this is the full differential of the variable z. This right hand side, maybe you may not appreciate it now, but this right hand side, it's what we have to solve, trying to get the actual function where these two terms are coming from. So the two terms that are actually, as you can see, one side is having a partial derivative of x, another side partial derivative of y. So together they give us one function. They come from one function. So this is what we have. If I may, so what we have here is that if we let dz is equal to 0, what will happen to the right hand side? It therefore means we can therefore have a dz over dx here plus dz dy is equal to 0, therefore, because dz is equal to 0. Now, maybe it's starting to be clear now that this is what we call the standard form into the exact differential equation, but maybe to actually even appreciate it even further, how about we do the change here that you allow the dz dx to, oh, it's written on top here. I think I don't have to even write it. I see it just above there. Let us do that. So what we see here is therefore means we have d over dx, therefore f of xy dx, it's a plus with a dy, therefore f of xy dy is equal to 0. Right? I think now we are all appreciating it, but even further, we can have here m xy dx, that's a plus, and xy dy is equal to 0, where I can then say, try to go down, so where we can then write that where m of xy is equal to the partial derivative with respect to x of this f of xy function, which we have to obtain as a solution, then n xy, it's a multivariable function, which is actually the partial derivative of the f of xy function. Right. So this is the kind of differential equation that you are facing. As you can see, this differential equation that we have here, it developed from a differential of the f of xy function, which is therefore our task now to obtain as a solution. So we have to go from this differential, we must recover the solution, this f of xy here. Right. But as you can see, there is a step where we see the dz equal to 0. So since the f of xy is equal to this z, now how will you recover z in this situation? So for you to recover z here, it will mean you must integrate left and right hand side. Therefore what will happen here is that you will have a z is equal to, therefore the constant, because there is a 0 on the other side, right? So that is why then what you will see is that the solution to this kind of a differential equation is always written as f of xy is equal to c, because when z is equal to c, therefore it means f of xy is equal to c. Then we normally will leave our answer in this situation. Okay, so that is a bit of the development of the differential equation you're facing. So I think it gives you some idea of what is going on here. Next thing that I think is important now is to then try to solve this differential equation. So this is what we will be having when we start solving this differential equation. This is the standard form of this differential. So how do we solve it? Then let us start. So we now have this. This is what we start with, which is the standard form. So the first thing when trying to solve this equation is to obviously have the standard form. Okay, so in the steps that I will write, I will start after we have the standard form. But again, please, the first thing that you must do, you must have this differential sitting exactly in this place. Let me even put a star, because now when they give you problems may be put in any other way, just maybe to confuse us. So you have to put it nicely in this position so that you are therefore able to figure out exactly what is your m function, exactly what is your n function. Okay, so this is what you must ensure first. Okay, so after we have the standard form, then what do you do? Okay, so the next thing that you have to do, I will say steps to solution now. So the next thing that you have to do after you have the standard form, I'll say number 1, check if the differential equation is exact. Let me say check. Say check for exactness. Check for exactness. Right, so how do we check for exactness? We use a simple concept. In multivariable calculus, where we're performing partial derivatives, there is a concept that we know which actually talks about cross derivatives, or say cross partial derivatives. It says, for instance, for this function here, maybe I don't write something general, it will say, for instance, here, because all our differential equations are just two variables, it will say the second partial derivative, cross partial derivative of the f of xy function, it says is equal to the second partial derivative. Now the cross, it means it's now a y with respect to x. So this is the concept that we use to test for exactness, right? So when we test for exactness, it means what you have to do yourself, you have to find, if you may allow me to omit the xy there, I'll just say my. you must find my, then you must find the partial derivative also of n, now with respect to x. Because what you say here is that, for instance, partial derivative of n function with respect to x, this is actually equal to, remember n is a derivative on its own, is a partial derivative with respect to y of this f of xy function, right? The derivative, the partial derivative of y, sort of m with respect to y, this is a partial derivative of originally with respect to x, partial derivative. This is where it's coming from. So this is a cross, right? So if the two partial derivatives are the same, they are equal, this therefore always implies to us that we are actually working with exact differential equation. This implies exact ODE. Let me write that. So this implies exact ODE. Okay, let me erase to make a space. Okay, so therefore means we're having exact ODE here. Okay, so now after we have checked that you're having exact differential equation, so what next? What do you do next? It therefore means you must obviously get the function f of xy, right? Get the function f of xy. There's two ways that you can get to this function. Both ways involve integration. So you can either integrate the function m dx, again, if you may allow me to omit the xy at the bottom here. You can integrate the function m with respect to x. If you do that, you must never forget your constant here. Another option is that you can also integrate. This is another option. Let me put this down. You don't have to do both. I know, depending on what you are using when you are studying, some books they integrate both, and we have to see. Maybe we'll talk about that when we continue. But some cases they actually say integrate both, but I don't think it's there as necessary. Is equal to n, then this will have to be y plus. There's something special with the constant that you have to put here. Okay, so you don't have to do both again. You can just do one of the two. Okay, then we'll discuss as we continue. So let us say then we decide to use m. We decide to integrate m first. Basically, what will tell you to decide whether you must integrate n or m, myself I always say, is the integral that you'll bump into, because you have to perform an integration. So if you see that the integral with the m will be easy, go for it. If you see that n will be easy, then let it be your target, because you will integrate very, very simple then. Okay, so what do we have? Let us use a variable q. Therefore it will be qy here. Then if this is your choice, then it will be q of x. The reason being a function here is that you put a function in position to recover some y-only terms that you will have lost when you was finding the partial derivative of x. Take for instance, say we have a function here, f of xy is equal to x y squared plus y cubed, right? When we are performing the partial derivative here with respect to x, y will be constant. So a term like this will be lost completely in the partial derivative of x, which is this m function that we're integrating. We will never recover it. So the partial derivative here will be here. So with respect to x, it means it will be y squared plus 0, right? So see, we have nothing. Then the partial derivative with respect to y, it will be 2xy plus 3y squared, right? So this is what we'll get. And these two, so these two partial derivatives is what you have. So these two partial derivatives is what you have in this differential equation, and you have to recover all the terms only from these two that you have as the m here and the n here. So now even yourself, if you look on the two values, the m and the n, which one will help you recover the x values? Which one will help you recover the y only values? Then which one will help you recover the terms which are the mix? Okay, I will tell you. The function m xy will help you recover the terms of this f of xy function which are the x only, and also the terms which are the mix, which is the x and the y, both together. Not to say a product like this. I mean the terms which had both, which had x and a y. Terms which had both. Terms like these ones. Cycle. So a term like this one into this f of xy, which are the mix, you can recover the term from either m or n function. Just by integration, you'll recover such a term, right? But a term which is having y only, you cannot recover this term from the integral of an m. You only will recover it from the integral of an n function. Because what will happen here is that this term will go to 0. So you'll never be able to recover with the integration. Right? And then, so what you have now is that the n function, this will help you recover terms which are y only and terms which also had a combination of x and a y. So those terms will be recovered here. So in any case, if your approach, you opt to integrate the n function with respect to y, so therefore you'll get both of these terms here. You'll get both of the terms which are the y and the x. You will recover them. So therefore, what is missing now, you will be missing terms which only had x. Then you must go into the m function and integrate only y free terms. You are done with the y, you only need x values now. So that is what you need. Okay. So that is what you need. Okay, so the next thing that we have to discuss now is then how do you get this, for instance, q of y or q of x. Okay, so let us say you opted to integrate m. Then we have a q of y as your constant. So how do you get this q of y? It's simple. The q of y, there is a longer form to this, but I'll just give you the shorter form. I think we did discuss the long form in class, so I'll just give you the shorter form. The q of y, as you can see, these are values that you only can recover from the n function. So therefore, be it, we must go into the n function. You'll have to integrate the n. Sorry, I think I did a mistake here. This must be q of y. Okay, q of y is this value here. This value, okay, sorry, is this value here, q of y. Okay. So the y values, you will recover them from here, then with respect to y, right? But of course, this is a multivariable function. N is a multivariable function with the n, x, y, which could be, for instance, 3x squared y, plus 2y, maybe like this. So your focus when you perform this integration, only focus on x-free terms. Let me put that statement here. Only focus on x-free terms. So for instance, if you have to integrate this term, there is an x here, so you must ignore. Therefore, your answer will only be, for instance, it will be y squared. So the terms which are having the x variable, you ignore them. You don't do anything to them. You only consider terms which are having y and some constant. Maybe say if your n xy here is equal to maybe say 3xy squared plus a 4 plus 2y like this, then in this integral you ignore this term, only consider the constant and the y only terms. That will be your answer. Okay, so as you can see, you can in fact put these two things together, this here and also this value of qy here, of this constant. How about we put it together? You don't have to do this, I'm just showing that. Let me just put it aside here, that I think I'll run out of space when I go this way. So let me try to bring it closer. Again, I just put it like this because you don't have to do both. You can do one of the two. So the full answer basically is m dx plus, here where there's a q, you can put it like this, and dy plus, you see now, this you only consider only x free terms. Right. So I think is this idea that you can integrate both, that in some cases, what you will find in other places is that they will say, let me put this in a square, I'll just write and erase this. They will say f of xy is equal to, m dx plus maybe qx like this. Then let's say same x also y is equal to, n dx plus qy. Then you have to put the two together because they are equal, put them together and figure out the values of q and y. So the terms which are, for instance, having both x and y, that you had to go through with some integration m, you have to perform integration again. Myself, I found it as a bit of a delay because you perform integration for something that you already know, you will no longer use. For instance, if we have recovered a term that is carrying both x and y here, then why must I perform integration for that same term also? Because I now have to ignore, I've already gotten the term that is having xy. So the focus now, when you go to this second integral, the focus must change only to recover y-only terms. This is what we are trying to recover now, y-only terms. So it's the same thing that if maybe you decide to integrate, say, f of x, y. Let me fix my handwriting. Say f of x, y is equal to, then you decide to integrate n, integrate everything. Then it's a plus, then your qx. Therefore, now your focus will be only, you have already recovered terms which are, n goes with a y, so that was a mistake. N goes with a y. Okay, so here you'll have recovered all the terms which were standing alone y, y only variable in this term. You also will have recovered the terms which are both x and a y in the same term. So what it could be e raised to x y. See this term having both, it have y and x. So you will have recovered these terms. So the only kind of terms that you are looking for now is a term which was having standing alone x. So say only had, say, y plus, say, the x only term. This is the x only term. So this is what you are looking for. So the terms, again, which are the y only, like this. Don't know, maybe it was a lean y, but there was just one y only in this term. This kind of term, you will have recovered them. We'll have recovered them from this integration. Terms which are the combination, you already have them. You are looking for terms which are the x only. Then that is why this is a q of x only function. So then you become selective when you integrate. You don't say waste your time. Okay, so therefore what we have here, we now are integrating m with respect to x, but again we are being selective now. We will say here y free terms. So y free terms mean your interest is in the x only terms and the constant. I'll say constant c. If there's a constant, you perform integration for those. Okay, so this is how you get your f of x. So after you have it, you therefore equate it into the variable c. F of xy is equal to c, which then is the solution. Then you stop. So the next thing, after we have the solution, so the next thing that you may have to do is that if you have some conditions that were given, then you may have to apply those conditions, then to get a value of c, which gives you a particular solution now, which then will be the end of it. Okay, so that is what you may have to do. So when you equate this to c, you don't change signs of your terms, right? You don't change signs of your term. You just say f of xy, for instance, say you try to find this function here, and is equal to 3x squared plus y. Okay, now you must say this is equal to c. It's not like maybe we are transposing things to the other side. No, you'll simply just say therefore 3x squared y is equal to c. That is the answer. You equate it. You don't change sign. Okay, so that is what we're saying. Right? That is what we're saying. Because the statement above, the statement said z is equal to f of xy, where the dz, which we set into 0, z was equal to c. Therefore, so goes f of xy is equal to c as the solution, because we set the differential to equal to 0 when we're getting the standard form. Okay, so the next thing now, so we're moving from here to the answer. Okay, that is what we have. Maybe I say we're moving from here to here, but z, of course, therefore we stop here. Right. So I think that will be it. Maybe next thing that we have to do now, let us bring in 2 examples, then we'll close. In fact, I think if one example will be nice. Let us see. Okay, again, there is a longer version of these steps, but we did that in class, so I will not repeat it. Okay, so let's bring in exercises. So this is our first exercise. Where is it now? Let us do this problem here. Okay, so the question is simply just solve the following differential equation, find a particular solution where possible. Just get this one, minus 2x dx, it's a plus, so it's a 2xy plus 1 dy is equal to 0. Okay, so there is no initial conditions here, so therefore we don't have an option to the particular solution. Let us just get the answer. Okay, so you will see it's very short. So the first thing that we have to do here, we have to perform the test, check if we have exact differential. Our m function is equal to y squared minus 2x. Our n function on the y side, dy, on the dy side is equal to 2xy plus 1. So what do we do when we perform the test? We go into the m, we differentiate it with respect to y. So this will give us a 2y, therefore have a 0. We go into the n, differentiate with respect to x. This will give us a 2y with respect to x is a 2y. Right? So what we say here is that the partial derivative of m is equal to partial derivative of n. Variables are not the same, so it's a y and a x. This implies we have exact ordinary differential equation. Therefore, we must apply the steps belonging to this equation. Now, which one can we integrate? It's up to us. Let us integrate m, y squared minus 2x dx, therefore plus q of y, because this was a constant when this partial derivative was being developed. We are fixing this differentiation because we know differentiation goes this way, integration goes the other way. So we fix what was messed up by differentiating with respect to x, we fix it by integrating with respect to the same variable to recover or to go back. Then we know also there are some variables which are the y only, which also got messed by differentiation. Then we'll recover them from n function by integrating with respect to y as well, because it's y that was being, of interest when the partial derivative was being performed. So therefore here with respect to x, therefore we get x y squared minus x squared plus q of y. And now we must recover this q of y. We will get this from the n side, which is n is 2xy plus 1 dy. And again, we are not just integrating anything here. Our interest is only on the x free terms, so that we don't waste our time integrating terms which we will not use. So therefore this is equal to, say this term here is having both x and y. I will not waste my time with it. Therefore it means we must only integrate this constant. Therefore the answer here is just y. Therefore we conclude, therefore means f of xy is equal to x y squared minus x squared plus y. Therefore in final conclusion, x y squared x squared y is equal to c. That is the answer. So there was no initial conditions, therefore it means this is the end. Okay, let us look at another one, which I think will be the last. I think 2 exercises will be enough. Number 2. So we have, so it's a 2xy minus 9x squared plus the open brackets, it's a 2y plus x squared plus 1 dy over dx is equal to 0. The same, there's a condition here. Yeah, they have a condition. It's a y 0 minus 3. Okay. Okay, so how do we solve it? So the first thing that we do here is that we must have a standard form. And in our standard form, this derivative is split into 2 differentials. Dy is there, dx is there. So we can do that first. We're having a 2xy multiplied by dx minus 9x squared multiplied by dx. So dx will be common in these 2 terms that we can put outside and say dx outside. So it's a plus 2y x squared plus 1 dy is equal to, when dx comes here, it will give us a 0 because there is a 0 there. So it equal to 0. So this is the standard form. The other differential also have the same standard form also, that it also requires the same structure, but that one we now have homogeneous functions. So after we have this, we are able to figure out exactly that the mxy function, there we have it, it's here, and then the n function, we have it, it is here. Alright? So when we perform our test, we therefore will say, with respect to y, because we know this is a cross derivative, partial derivative. This is therefore with respect to y, so this will be 2y, therefore 0. With respect to x, it will be 0 there, so 2x plus a 0 also there, so it's just a 2x there. I think you can obviously see I did a mistake here. I will say with respect to y, this is a 2x. Okay, so therefore what we see here is that my is equal to nx, and when this happens, it implies exact differential equation. Now, how do we solve a differential equation which is exact? We just follow these steps. Exact differential equation, and since I had integrated with the m first, we saw the answer, it was fine. Let me just integrate with respect to y now. Just for the sake of it. So it will be, therefore, we have a 2y x squared plus 1, then plus q of x. Therefore, we plus q of x. The x function that is in the q of x, what we know is that when this n was being developed, x was a constant. So the terms which were having x only suffered, they got lost. So we are trying to recover those functions which were x only. The constant, we recover them with the integration constant, because the function, for instance, could be, x y squared plus, maybe say x squared plus y squared plus a 4, right? So the terms that we have here, we can recover these terms for a term which is having a combination. You can recover this term from m and n. So this term will appear in both m function and x function, these functions that we have here. So those kind of terms will be recovered from either m or n. The term here, which is x only, can only be recovered from a m, because in n, x will be treated as a constant, and so it will give us a 0, and so it lost. We cannot recover x only terms from integrating the n function. We only can recover x only terms from integrating the m function. If we are the x squared, when developing m, this will be 2x, but when developing n function, this will be 0. It lost. And then the y only terms will be recovered from the n function. When developing the n, y squared will be 2y, so you just have to perform integration. But when developing m, y squared will be 0. It lost. We only can recover the y only terms from the n function. Okay. The terms which are having a constant will be lost in both n or m. So when you are developing the m function, a constant is forever just a constant, so 4 will be 0. When you are developing the n, remember these are derivatives, partial derivatives, 4 will be 0 still, which is the issue. We only recover a constant from the constant of integration, which we put as f of xy is equal to c. So all kind of constant will be sitting there. Okay. So therefore, so that is why then if we have set f of xy is equal to, you integrate, say, m for instance dx, then here you will recover two types of term. You recover the terms which are x only and x and the y. We have talked about this. So therefore you will recover these kind of terms, this one and this one. Let me use a different color. You will recover these two terms, x only and the xy terms. This one will be recovered from this one integral. Then you have a plus qy. In this qy, you will perform integration with respect to y, but again, you are very strict now. You'll say x free. You are done with the x. You say x free terms, and then what will happen now is that here you'll recover terms which are y only. All the y only terms will come and sit here. Okay, so that's what you need. Oh, what happened? Okay, so let's try to finish this problem. So therefore here, q of x is equal to, therefore it's a 2xy minus 9 x squared dx. Again, remember, now we are y free. So y free terms. So therefore q of x is equal to, therefore it means you must ignore this term, we don't need it. Therefore q of x is equal to minus, so it will be x cubed over 3 x cubed. Therefore f of is equal to oh sorry, we had not integrated the y. Let me write it here as equal to y squared plus x squared y plus y plus q of x. The longer version which I mentioned, it involved getting this function and then come back and differentiate with respect to y now is equal to, therefore differentiate with respect to y now, all of this right hand side, all of this y squared, x squared y plus y, plus q. Let me cut it here and say plus q prime of x. Then equate this whole thing. Sorry, it's a qx means we differentiate with respect to x. Then you equate this thing. It means you now have to equate it into the m, and then the derivative with respect to x here, it means it will be 0, etc., etc. There it will be alive. This one will be 0. And then there will be some terms here. Okay, for this case, it will be 2xy, and then a plus q prime of x, etc., like that. And then you equate it into the m. In this situation, m was, it's a long way, so m was 2xy minus 9x squared is therefore equal to 2xy plus q prime of x. So see now, this term is having a combination of x and a y. We definitely know that it will cancel. So q prime of x will be equal to minus 9x squared, etc. Then you integrate with respect to x, with respect to x, and what do you get? So you can see it's long. Therefore q of x is equal to minus, therefore 3x cubed. Then you take it, then you put it where it belongs. Okay. So this, I think, it's a long way. Of course, when people write tests, they don't follow the same steps, so maybe yourself will be following these steps. Let us conclude our problem. So it's a y squared. I'm taking this, writing it down now. Then the q of x. I have the q of s right here. So it's a x squared y minus 3x cubed. Therefore, we conclude therefore y squared x squared y is equal to c. Okay, so this is a general solution. This problem had some conditions: x0, y minus 1. So y is, y is minus 3. Y is minus 3. X is 0, means there's nothing there. Y is minus 3. X is 0, there is nothing also here. Is equal to c. Therefore means c is equal to, so it's a 9 minus 3. It's a 6, right? X squared is equal to 6. Okay. So therefore this is the particular solution we are getting. Okay, so I think that is enough for this exercise. Let us close it here. Then we will look in homogeneous differential equations in the next recording. Okay.